Now it's time to move to our first speaker or event for Bronze 183. So for me, it's my great pleasure to introduce to Dr. Edmund Puljak. Edmund Puljak is a quantum algorithm expert and Planck QC working on quantum and quantum-inspired machine learning for real-world application. She completed a collaborative PhD degree between CERN at Barcelona Supercomputing Center and Universidad Autónoma de Barcelona, focusing on improving anomaly detection methods using quantum and tensor network techniques for medical image and high-energy physics. Passionate about science communication, she regularly delivers access of talks and tutorials on quantum computing, tensor networks, and quantum machine learning. Today, she will give a talk titled Friendly Introduction to Quantum and Quantum-Inspired Machine Learning. Dr. Edma, the floor is yours.
Hi all, thank you. Let me share the screen. Okay. Second. Okay, do you see the front slide?
Yes, we can see it.
Okay. Okay, so today I will give a small introduction to quantum and quantum-inspired machine learning. So I am a quantum algorithm expert, or actually I am a quantum-inspired machine learning expert more in detail. At Planck QC, it's a quantum computing company in Munich, and we are developing neutral atom quantum computers, and I am working on the algorithmic side. Just to give a brief introduction to myself. So I started as a junior software developer, which was kind of like my side job during my bachelor thesis. I finished computer science, both on bachelor and master. And I was also doing some small machine learning internship at my university. And then at the end of my master, I got a technical internship position at CERN, and I was doing machine learning for particle physics. And that was my first encounter with particle physics. I was mostly learning machine learning by then. And then after that, I got a PhD position at CERN and also at University Autónoma in Barcelona. And I did a PhD. Was a collaborative PhD between these three institutes, and then and the topic was quantum-inspired machine learning for high-energy physics applications. So it was basically like a practical PhD. So I was developing theoretical stuff and then applying it to some practical applications. And then at the end of last year, I joined Planck. So I basically joined Planck before I finished the PhD. And that's in the summary. And now I am working in Planck as quantum-inspired applied machine learning engineer. I would say more detail. So today I will give an introduction to what is machine learning, classical machine learning, then what is quantum machine learning, and how quantum computing intersects with machine learning. Then I will introduce quantum-inspired methods. In particular, these are called tensor networks for machine learning, and give some practical examples. Then I will introduce quantum machine learning methods that include data encodings, variational models, and hybrid quantum classical pipelines. And at the end, just to mention some software packages that you can use if you want to develop it in code, and the open questions of this field. So first, the classical machine learning. Am I too fast? Just tell me. Okay, I guess not. Okay. So classical machine learning. So what is machine learning? So basically, it's a set of techniques that that computer needs to learn to perform the task without being explicitly programmed to do so. And to do these tasks, you have a few ingredients of a learning problem, which is data. So you need to have some data. You need to model this problem you want to solve, and you need to optimize your problem solving to get to some kind of solution that you want to answer some question. Okay. So your data can be in sets of inputs and labels, or you can also just have unlabeled inputs, for example, images. And then the labels of the images could be cats, like some food or something that you label the image with. The models, so they can be deterministic. I will explain what that means, or probabilistic. So deterministic means that for a specific input, you get a specific output. So there is always that one output for one input. And probabilistic means that the model is outputting a probability distribution. So that means, for example, if you have an input, you will get a list of probable outcomes for what can happen for that input. Okay. And there are different types of the problem of the models in machine learning. And in this today, I will mention supervised learning and unsupervised learning. There is also semi-supervised reinforcement, but these are more simpler cases. So supervised learning is this deterministic model. So basically, you have an input X that is mapped to a output epsilon, and the mapping is exact. And during the training of the model, you know what are the correct answers, and then you can lead your model to get better at getting the outputs. And we can distinguish the model for classification and regression. Then you also have a probabilistic type of the model for supervised learning. So basically, you can either have this full probability distribution, which means that the model learns the entire picture of the input and outputs, or you can have a conditional distribution, which says that given some input, what outputs are most likely to get. Okay. And then there is unsupervised learning, which actually guides the model to learn the pattern on their own. So there is no correct answers provided, and then the model needs to basically learn the pattern of the data, to learn what is normal, what is weird in the data. And like actually, when you get some unknown input to the model will learn to compare this input to everything else that it learned so far. Okay. And finally, in order to select the best model, you need to have an objective function, which tells you the quality of the model. And actually, it measures how model is wrong or by trying to give some output, okay? And you also have a risk minimization process, which actually tries to minimize this wrongdoing of the model. So it tries to adjust the model to be best at picking the correct answers. Okay. So how this translates to quantum machine learning? Okay. So what is the role of the quantum in this? So the quantum computing actually gives a different approach for solving the problems. And what does this bring us? So what are the goals of this quantum machine learning field? So basically, with quantum machine learning, there are some possibilities to kind of try to prove practical quantum advantage. In some terms, this means that basically quantum algorithms can be better than the classical, but there is a question mark on this because we still don't understand, is this the correct goal as well? So basically, we try to answer when a quantum computer can solve machine learning models faster or better. Okay. Then maybe another approach that maybe it's also like more natural to me is that we want to find new use cases which are natural for quantum computers and then that cannot be solved with classical machine learning. And then maybe this is another goal of quantum machine learning. Then we can develop new optimization algorithms that use quantum methods to optimize either classical algorithms or some new examples of machine learning algorithms, or we can also improve existing machine learning algorithms or something else. So there is a lot, at the end of the presentation, you will see there is a lot of unanswered questions, but it's good. So this keeps us going in this field. Okay, so how the quantum computing intersects with quantum machine learning. First, I will give a visual example of what is like how you can connect the techniques in classical machine learning with the quantum computing. Okay, so this is maybe like a bit complex picture, but I will try to explain it in detail. So kernel methods are methods from from classical machine learning, where actually if you have some data and you cannot solve that in a classical space, you can actually move them to like a richer, higher dimensional space where the problem becomes easier, and then maybe they will be separable. You can solve the problem there, and you basically map it to a higher dimension, and this is this transformed feature space. And you access this computation via kernel. Kernel is like a mathematical function. So, and this gets mapped to a quantum computing, and it's basically a quantum computing equivalent where you have some data space, which is the same data space. You need to encode this in the quantum state, and then the transform feature space from the classical kernel methods is called quantum Hilbert space, where you have exponentially many dimensions. And then you access not via kernel now, but via measurement. So basically you need to extract this information by measuring a quantum system. Okay, now this feels very complex, but by the end of the presentation, I will dissect this into parts. Okay. On one side, we have quantum computing, and then on one side, we have machine learning. And what are the intersections? So you can have classical data, you can have quantum data, then you can have a type of algorithm which is classical or quantum. So how do we intersect these? So classical data means that you analyze and process classical data with classical but quantum inspired methods, and I will introduce these today. These are called tensor networks. They can be used to simulate quantum systems or actually used in machine learning to perform a learning task. Then if you have classical data, you can, for example, have an image that you encode in a quantum state, and then you analyze it with a quantum algorithm. I will also give an introduction to this. Then you can have a quantum data. For example, it can be like a description of a quantum system. This is a molecule, but it can be a quantum system. Then you can use tensor networks, for example, which are classical but quantum-inspired methods to process the data. Or you can have quantum data and analyze it with the quantum algorithm. Okay. And today I will focus on these first two. First I will introduce the tensor networks or these quantum-inspired methods, as I said before, and I will give you a few practical examples. Okay. So, first of all, a tensor. What is a tensor? So tensor is actually a vector matrix, or it can be a higher order tensor. And in the tensor network notation, we describe it with a circle and a leg coming out of the circle. And this I is the dimension of the vector. So the vector is a circle with one leg. Matrix is a circle with two legs because it has two dimensions, and then a three-order tensor has three legs, and etc. And now, just to connect these with neural networks from classical machine learning. So this is just a very, very simple neural network from classical machine learning. You have input layer, hidden layer, and output layer. And today, I will try to explain the input layer as a big tensor that we will represent as a tensor network. Okay, so we take this layer, we call it a layer tensor, and we can perform a series of singular value decompositions. I will not explain what is a singular value decomposition now, but basically you take it and then you factorize it or break it to a chain of smaller order tensors, and then now this is called the tensor network. It will be more clear later. And now this chain is basically representing the same information, but it's less computationally expensive. And how is that? I will make it clear. There are two types of parameters in the tensor networks. So you have bond dimension, and it's a dimension that connects these two tensors, and basically it explains the amount of correlation between the two neighboring tensors. And you have a real dimension, or in physics, it's called a physical dimension, that basically can be connected with some input embedding. I will also show an example of that. And this is called a tensor network. So a big tensor can also represent one layer of a neural network, but it can represent also a quantum state. So a quantum state then can be represented with many types of tensor networks. First, this is 1D, so it's a chain. You also have 2D tensor networks, or tree-like, or even more complex structures, depending on what you want to model, what is your learning problem, and how we can use tensor networks for machine learning. So here I put a brief overview. On one side, you have quantum machine learning, and then on the other side, you have classical or hybrid machine learning. Because these tensor networks are classical models, but they are inspired from quantum because they were firstly used to describe quantum systems. So in the quantum machine learning, we can use them to benchmark quantum algorithms. That means that you can represent some quantum algorithms as a tensor network. And then if the performance is comparable, then you also question yourself, okay, why do I need quantum when I can use a tensor network? Or they can be used to simulate quantum systems, quantum systems in chemistry as well. Or for classical and hybrid machine learning, they can be used for classification, anomaly detection, any basically machine learning task that you have in classical machine learning. And now I will kind of introduce them more in detail. So how we can use them as machine learning models or AI models. So you can train a parameterized tensor network as you would train a neural network to perform a task. And this kind of comes in a pipeline format. So if you have some data, you need to represent your data in a tensor network-like format. Then you introduce it to a parameterized tensor network. You train a tensor network with sub-optimization technique, and then you evaluate your result. Here is the paper that describes this pipeline in detail, and also one of the packages for this type of learning. Then, for example, you can compress your data with tensor network, and then you can attach it to a neural network. So it's kind of like a hybrid structure. Or you can use tensor networks to compress layers of neural networks. So to basically represent layers of the neural networks with less computationally expensive structure, which is a tensor network. Or you can have a hybrid tensor network neural network structure. So the first part, I will give a small example, like a very simple example of image classification. So if you want to classify images, for example, these are these NIST images that you have 10 classes of images, so from 0 to 9. You want to take this image and you want to first represent it as a tensor network format. So basically, this is an image. You take each pixel, and if you remember from before, you need to put it to a higher dimensional space. So you can do this with the embedding function. And this embedding function defines this real dimension or physical dimension that I was mentioning before. And now this looks like this. So basically, it's a large feature vector that each pixel now has not one value. It's not a scalar anymore. It's a vector of two values. And after that, you would initialize a tensor network randomly or any initialization technique. In this case, this is called a matrix product state. It's a one chain of tensors. And you can see that it also has a physical dimension too, because it needs to be connected to the input. And you want to basically perform a classification, and then you will output one vector of classes, which is basically C is 10 in our case, because we have 10 classes, and the highest value of this vector output will give you what is the class of this input image. So in the case of the 4, on the 4th place in this vector, we will get the highest value. Okay. And these are just some references for you to look at this example. Okay. Okay. Then we can compress. How do you compress a neural network layer? So if you take one layer, this is the weight matrix. So you can represent it as a matrix. You take, and this has m square number of parameters. This is just because later we will compare the tensor network representation. Okay, so you take this matrix. This is the tensor network notation. As I said before, it's a circle with 2 legs because there is two dimensions. For the sake of this example, it's going to be 216 because it's easy then later to reshape it. You reshape this to have 6 legs now. So this is just a reshape operation. Then you can split this using this singular value decomposition. It's a decomposition that factorizes it to a chain of smaller tensors. And now these tensors are 3 or up to 4 rank. And this is way less computationally expensive than this 6 rank tensor. Okay. And in the terms of the number of parameters, because we also want to see if this is being compressed, right? So this has 216 to the power of 2, and this has so three tensors times 6 squared, because you have a physical dimension up and down, and then bond dimension square. And if you put bond dimension 10, this has like a lot less parameters. Okay. And this is in a general case. So on one side, you have large rank tensor, which can be either a quantum state or also a layer of a neural network. And on one side, you have a chain of smaller rank tensors, which is the tensor network representation. Then the last part is that you can have this hybrid structure. So basically, you optimize jointly neural network and tensor network in a pipeline, okay, for a specific task. And now we switch to the quantum machine learning methods. Take all this as like an overview of all the methods there are. I know it's a bit hard to follow, but I'm trying to introduce everything on like a higher level and put a lot of references so you can go and look into it. Because basically for each of these parts, I could have another lecture. So for the quantum machine learning, so this is how a quantum machine learning pipeline works. And I always try to look everything as a pipeline, because then I can dissect parts and explain each. So first you need to encode your classical data to a quantum state. And then you take this quantum state, you perform some operations in a quantum algorithm, and then this quantum algorithm can be used as a machine learning task. And then at the end, you perform measurement to have some kind of output. Since quantum mechanics is actually a probability theory, then you need to repeat the process ideally infinite amount of times, but a lot of times to make sure that you got the correct desired output at the end. So you need to gather statistics, okay? And at the end, you have the output of the algorithm. You use this output to optimize the process, and I will explain each of these parts in detail. So the first is you have this encoding. So in the classical machine learning, if you have some data set or some input, you process it with a machine learning algorithm, you get the output epsilon, okay? But for the quantum, you have some data set or input X, you need to perform the input encoding, process it, read it out, and output the epsilon, and you need to repeat this process. Then there is also something called the state preparation and evolution, but this is concerning quantum systems, okay? And today I will discuss first this input encoding. So what are these encodings? So the encodings are very crucial to the success of the quantum machine learning algorithm because they limit what the quantum machine learning algorithm can learn. And basically, you need to choose the right encoding strategy because it determines everything else in the algorithm. Does it fail or not? And you can actually encode either a single data point or entire data set in the quantum state. And you need to find an efficient encoding scheme that actually scales well with the problem size. All this looks kind of like a very vague, but this is maybe the most important part of the whole pipeline. Okay. If you remember from before, this is just a representation of the quantum state on a block sphere. So basically, you have states 0 and 1, and it can be in a superposition of these two states. I think you know this as you had the previous lecture. Okay, so there are many types of encodings, but here I will just introduce three most important ones. So you have a binary encoding. So what does this mean? That means that if your data is represented as a bit, then you can just map it to a qubit, and it's very simple. And because every bit gets mapped to a qubit state. Then if you can have a rotation encoding. That means that if your data is real or complex, for example, each pixel of an image can be a rotation angle on this block sphere. Okay. Or you can have a vector encoding, which in our case, we call it amplitude encoding. That means that these pixel values, for example, are encoded in the amplitudes of the quantum state, and you use this type of encoding also for the real or complex type of data. And if you remember this image from before, basically your encoding is the first part. So going from the blue data space to the Hilbert space, this psi is actually the data encoding, and you access at the end the information of the whole algorithm by measuring the quantum state system. And this brings us to one of the very interesting characteristics of the quantum models is that, for example, if you have a vector of inputs, let's put it like this, you encode it in a quantum state, and for example, you rotate it by some value, and you continue rotating it in some quantum algorithm. At the end, basically, you have encoded data, you pass it through a quantum algorithm, and you measure it. And all this is actually everything that happens in this quantum algorithm is linear. So, and at the end as well, when you measure it, you see that there is kind of like a linear boundary between -1 and 1. So basically, all the transformations that are happening on the qubits in the quantum algorithm are linear. And if we go back from the slide before, these linear transformations are happening with these quantum gates. And if I have time in the backup slides, there I have like a schematics of what does it mean if you perform one of these gates on a qubit, how the state changes. And basically, these quantum algorithms can be machine learning models. But first, I need to connect these quantum algorithms with tensor networks. So you also know in the back of your head that they can be represented with tensor networks. So, and these are also called quantum circuits, actually. So to connect these variational quantum models with tensor networks. So this is a tensor network from before. It's a chain of tensors, okay? Then you can represent this as a ladder structure on a quantum circuit. So basically, if the bond dimension is 2 between two tensors, that means that this is a 2-qubit gate, okay? And I linked here the paper that describes this in more detail. And both of these tensor networks and quantum circuits can be machine learning models. And now, what are these variational parametrized quantum models? So if you remember from before that we had this deterministic, probabilistic, supervised, unsupervised learning. So now I will introduce them in the same way. So parameterized quantum circuit, or how sometimes they are called quantum neural networks, they can be deterministic and also probabilistic models. This is a very complex image, and I will explain it in detail. And today I will actually describe more in detail the deterministic quantum model, because I can give a nice example on that. So the deterministic quantum model. So basically, you need to produce a deterministic label, but since you all know that the measurement is not a deterministic process, it's a probabilistic process. So how you actually do that? So so I will explain this in detail. So you have a quantum circuit, and the first part of the quantum circuit is the data encoding scheme. As I said before, you have some input, you need to encode your data, and this is this S, or the green part. Then there is the W, which has trainable parameters, and these are the gates with trainable parameters that you can train. Eventually, I will say how. And then basically, how you prepare a quantum state is that you take this circuit, which consists of the purple and the green part, and you apply it to the zero state. Zero state is like an initial state. And how do we get some output from this algorithm? So we need to perform the measurement many times to get some output, right? So basically, we need to get the expectation value of this measurement, which is represented with these brackets. And how you will get the output of the model, I will give an example later. And then this is actually your variational or parameterized quantum model, where variational means that variational can be trained. Parameterized can just be like a quantum model with parameters. Okay. And this is represented with this function. So you want to get expectation value of the observable operator M. That represents basically what are you observing. So it represents which answer you want to get with this output. So just to give a visual example, because there is like very big terminology here. So as I said, these brackets are the expected value. And you will need to perform some statistical operations before, after many measurements. For example, we can average many measurements. And the more outputs you collect, the more you are sure that the output is accurate. So for example, if your algorithm has 5 qubits, and at the end, you want to measure each qubit, and you collapse it to be a classical state. And this is the output of 5 measurements, for example. And you want to find a probability of finding the last qubit in state 1. And when measuring, this will be your prediction. This is just a very, very simple, a bit stupid example, but just to see that, okay, you can search for this and you get this prediction, and then you also know how sure you are of it, or how many times you perform the measurement. Okay. So how we optimize this algorithm? Okay. So basically, we come to this hybrid quantum classical pipelines then, because they are used to train these quantum models. So how you train machine learning models? So you have some objective function that depends on the model F, and model F actually contains these trainable parameters. But how you train quantum machine learning model is that you need to find the measurement that minimizes the objective function that depends on some model F, and then F contains these parameters. Okay. So if you do it with gradient-based methods, which are the most commonly used methods in machine learning, you need to calculate the partial derivative of this cost function with respect to some parameter. This is the mu here. This part, the first part, can be done with classical automatic differentiation libraries. So PyTorch, TensorFlow, all these machine learning libraries. But this part is actually a quantum computation. So how do you actually compute this part? So there is something which is called parameter shift rule. Basically, you want to try to find this gradient update. Okay. So how you do that is that you run the circuit twice, but each parameter in these gates is shifted by some microscopic shift. And then at the end, you basically, your partial derivative is basically just a subtraction of these expected values of these two runs of the circuit. And you repeat this for every parameterized gate in the circuit to get the gradient, basically. So this is the estimate of the expectation value for each run, and you get the estimate of analytic gradient as well. And you use this gradient estimate later to include, to use it in a hybrid quantum classical pipeline. So what does this mean? So basically, here, so the blue part is quantum. So you run your quantum algorithm, you get some measurement and output, and then you use either gradient-based optimizers or gradient-free methods to classically update parameters, and then you put it back to the quantum, and then you perform you circle it. And why this is done is because today quantum computers are very noisy. So you cannot do this optimization online on a quantum computer. So until they get error corrected and very stable, this will be done most likely in this sense. Okay. And at the end, this software packages and some open questions that we are left with. So since you train the quantum circuit as this hybrid quantum classical pipeline, you can use machine learning libraries like PyTorch, JAX, TensorFlow. Then for the quantum softwares, there is PennyLane, Qiskit, Cirq, Yao is in Julia. And then for the tensor networks, there is Quimb, Tenet is also in Julia, Tensor Crouch is in PyTorch, and then TN4ML is in JAX. And then you can choose, in my case, the TN4ML uses Quimb. In my case, Quimb is the best one to represent the tensor networks. And what are the open questions? Okay, so how we still are not sure fully how to fairly compare quantum and classical algorithms, because we need to understand, like, do we want to achieve advantage to beat the classical algorithms, or we just want to find the new use cases? So this also reflects on how fairly we compare them, right? Also, how do we find well-defined parameterized quantum circuits? Because we mostly think of the classical data and we embed it in a quantum state. That means that the data embedding is the most important part. But does this limit us to some way in choosing the quantum algorithm later? There is like many open questions on this topic. And also what this quantumness brings to AI. So basically, like, does sometimes when you use quantum, you basically overcomplicate the problem, maybe? So where is the good ratio between adding quantum or just using classical machine learning? We still also don't know this. And later, when the error correction gets to a nice in a nice place where everything is very, very error corrected and the quantum computers are stable, how this will change the quantum machine learning algorithms, the scaling of them, also it's an open question. And this is one paper that I really like from Maria Schuld, and they are trying to tackle the question of, is quantum advantage the right goal of quantum machine learning? So do we actually want to beat classical machine learning algorithms, or we just want to find some new use cases that are not tackled with classical machine learning? Okay. And here there's many references for the papers, but there is many more. Most of this talk is basically a lot of the, if you saw on the slides that I put this Maria Schul, the first machine learning with quantum computers. It's a very nice book, and in my opinion, like very, very nicely described. If you know something of machine learning, you can study easily the quantum machine learning from there. And that's it, I think. Thank you. Now I can answer all the questions and go back to the slides that if you had some questions during the talk.
Thank you, Professor Emma, for your beautiful presentation. We had a couple of questions for the public. The first one is, your work connects quantum algorithms, tensor networks, and machine learning. What motivated you to explore this intersection, and what problems excited you most when you started working in this area?
So yes, I started to work on quantum machine learning algorithms, just quantum. But then at CERN, since I was doing it at CERN, I saw that tensor networks are kind of like quantum-inspired versions that we can use to later be ready for the quantum algorithms, but they can be actually put on the, for example, FPGAs or chips that we use in the detectors, and then the data can be analyzed with them. So I kind of find my way to basically try to solve problems first with tensor networks, and then eventually we can prepare for the quantum algorithms later. That's why I find it interesting, because I can see the progress right now. That makes sense.
Okay, we have a second question. This is for Saba. How far away would you say we are away for genuinely quantum machine learning?
Can you repeat? Sorry, I lost you for a second.
Yes, yeah. How far away would you say we are far away for genuinely quantum machine learning? A tensor for application.
For applications of quantum machine learning?
I guess that is concentrated question. Yeah.
For real applications of quantum machine learning. Oof, I don't know how to answer that really. Because there is many nice things that is going on in the research. Yes, I don't know how to answer that. Like that's why I can tell you for the tensor networks or the quantum inspired that they are already being used for some tasks as I introduced today. But for the quantum ones, for the optimization part, yes, there are good things happening there. But in general, like I think it's still like research in developing.
Another question is, for your perspective, what should be the community prioritize in the next few years?
That's also like an open question. Yes, it's an open question. There is many. So if I go back to this pipeline of the quantum, this one. So there is many parts of this that people are researching. So also encoding different structures of different quantum algorithms, how you optimize, also what are the obstacles in the optimization, like some of these barren plateaus problem. So I think it's a nice direction that like a lot of these parts are being researched also jointly. So I think like the field is developing quite nicely. It's just that there is many directions still. So I also don't know how to specify, like I don't have a correct answer to that.
Okay, thank you for the answer. So another question for Arturo. As a woman working in quantum technologies, what advice would you give to young women around the world who are interested in entering the fields like quantum computing? physicists, or artificial intelligence?
Mm-hmm. But I think so. I would always suggest if you like something and something like it's your passion and you enjoy doing it, you enjoy learning something. I think you always need to go for it. There is like I think now there is a big community of girls and women in this field, or at least I can feel that. I also during my PhD, I was also surrounded by not many men anymore, because also I come from computer science, so there is a bit more equality now in computer science as well. So I think it's like you don't let some I don't know. So if you really enjoy something, you go for it, and I don't think anything can stop you really. There are many problems on the way, yes, as a woman, but I think now you can, there are many communities for that. You can approach many people with any problem. So I think I would say, why not?
Wonderful. So we had another questions. So what originally inspired to you to pursue quantum computing and machine learning as your research direction? Was there a specific moment, mentor, or experience that influenced you?
Actually, so I always liked machine learning. I would, if I never start to learn quantum computing, I would just continue with machine learning, and then I would probably do some research in AI. But at the end of my master, I was there at CERN. There were some lectures in quantum computing, so I just took it out of curiosity. Like, I also never heard of quantum computing. So basically, when I started to learn quantum computing and anything related to that was just at beginning of my PhD. And before, so at the end of my master, if I didn't take this class, I would probably continue doing like research in AI, which is also interesting in some sense. And but quantum machine learning I like because it's something new, and it's exciting because it's new, and actually it's exciting because we don't know all the answers. That's why you research. So yeah. Is there any other question?
Thank you very much. I think that Dr. Brulio Vegas has some connection problems. He's back.
Okay.
Yeah,
Okay.
I'm back. So sorry.
No
These
problem.
technical problems we had sometimes for the internet. So in this case, Professor Emma, it looks like there's no more questions.
And there is one.
Let me check it out again.
There is one. Hiring is in general quite tough. How do you recommend younger professionals stand out? Do you need a PhD to pursue the jump in quantum? So I would say many people where I work have a PhD, but also a lot of them don't. They were just doing masters. So I would say that you need some master in quantum technologies at least, then, if you don't want to do the PhD. But a lot of like pure research, maybe it would be better to have a PhD. But if it's some quantum engineering position, then master is also enough. Like then it's just about your experience and what did you do? Did you go to like some internships and stuff like that? And I know it's quite tough. It was tough for me as well when I was looking for jobs. But one thing that I would suggest is so when I was looking for jobs, I found one was the name of this, like the person who prepares you for job interviews. So basically you need to learn how to sell yourself, and that's all. So and how to write a nice CV and stuff like that. So this is very helpful. It's not a recruiter. It's no, not a recruiter. There are special people doing this. To be honest, I forgot the name in English. Mentor. Yeah, I forgot the name. Sorry. Headhunter. Wait, I will find it.
Thank you so much, Professor Elma. Thank you for accepting. Oh, then we had another question. Okay, this is for Villa. I am actually working in Cool Atom interferometry field. I had an interest in quantum computing as well in machine learning and quantum machine learning also. So it will be a good decision for me to go in this direction.
I mean, yes, if you want to. So did you do any machine learning before? I cannot answer that for you. It's kind of like if you're interested enough in that direction, that's a good direction for you. Like I also didn't know if this was good direction for me. I just was doing things that I was interested in. So I guess yes. Cold atom interferometry field, is that like more experimental? You can do experimental quantum machine learning as well. I have some also friends doing that. So
okay, perfect. So here we now have more questions for our speakers. So thank you, Professor Elma. We really appreciate that you accepted our invitation to give a talk on our event, especially knowledge for Mariana Filipova, who is leading in the cool Bulgarian quantum computing team in Bulgaria. So also for Cubic Hub, we appreciate that you accepted this call. I hope to see you in future events.
yeah, thank you for calling me. Yeah, it was a pleasure.